I'm really happy to be here this year to tell you about some recent work I've been doing. So my name is Greg Snyder. I've been at the Space Telescope Science Institute for 5 years as a postdoc, and next month I'll be staying on at Space Telescope to join the staff of the Mikulski Archives for Space Telescopes. And one of the visions that I have in my new role is to better integrate all of the ambitious cosmological simulation work that we've heard about at this meeting with much of the data that we're taking with HST and hope to take in the future with JWST and with WFIRST. And the topic I'm going to be talking about is trying to understand galaxy merger rates in the distant past. And this is work that's been done in collaboration with a handful of folks. And Vicente and Amanda are also giving talks in this conference, so stick around for those. And the motivation for this comes down to the fact that early mergers in massive galaxies might be responsible for forming and transforming their major properties. And so this is a plot of a sort of a cartoon diagram of the galaxy merger rate as a function of look-back time or redshift. And our cosmological simulations for many years now have predicted a very simple form for the galaxy merger rate, which is the number of mergers per galaxy per unit time, that it is low today and rises pretty steeply into the distant past. And so that's the purple curve here. And I think I, for one, in much of my career, have assumed that this is true and that this must be happening in the real universe. But really, only the last 10 billion years or so have we had sort of in-depth data analysis from our surveys with telescopes that either confirm or hint strongly that this is the case. And so what we want to do is actually peer back further with the abilities of the Hubble Space Telescope to understand the galaxy merger rate in the even more distant past. And so to summarize my talk before I start, I think what we're seeing in the CANDLE survey in particular is that as we look back from redshift 1 to about redshift of 3, the data imply an increasing merger rate, as expected, which is nice. The evidence for this comes both from early stage close pairs, which we heard a little bit about earlier in the session, and late stage mergers, or the final coalescence of the nuclei in the galaxies. And the interpretation of this really relies heavily on using large simulations to map data to real events. As Joel mentioned earlier, we need to understand the observability time of any particular physical process if we wanted to make inferences like this from data. And so you may have heard about a puzzle that emerged over the last 5 or 10 years or so, which is that if you go and measure the mass-selected close pairs in HST data, the trend flattens out about 10 billion years ago. And so the data roughly correspond to this, where the prediction is a factor of 5 or 10 higher at a redshift of 2 than we were measuring. And so this is a procedure that relies on knowing the observability time. And so to understand whether this might evolve in a way that we didn't expect, we took the Illustris simulation, this is Illustris 1, and sort of used it as a direct analogy to our pair surveys. And so we created mock surveys. There's just an example of one, a tiny slice of a mock survey with the James Webb Space Telescope here to understand and create apples-to-apples measurements from the simulations to try and interpret this puzzle. And so many of these surveys, sort of example images and catalogs are available in MAST, and so you can go and download and play with the data yourselves if you want to do similar studies on these. And we really wanted to understand why weren't these merging pairs more common. So we made a direct comparison with the simulations where we have both access to sort of forward modeled data space on the left, but also the intrinsic evolution of each of the sources, and we can ask whether or not they're actually mergers or not. And when you do that, we found actually really striking agreement between the pair fractions measured in the cosmological simulation mock surveys and the data with HST. And so what that strongly implies in my mind is that the observability time must be falling rapidly with look-back time. And so originally we were assuming a constant observability time, but actually an observability time that scales with the age of the universe pretty simply is provides much better agreement between the intrinsic 3D merger rates and the projected pair counts as a function of cosmic time. And so you can see the first conclusion of my talk is that pair-selected merger rates are expectedly high at about a redshift of 2. And this really relies on a lot of careful analysis from others like Hamaswara, Alison Mann, and many others in the CANDLES collaboration to really pin down the statistics of this as a function of cosmic time. And I think this is one, plausible interpretation for the data that we've seen. In parallel with our efforts to understand the pair fractions as a function of cosmic time, we've been pushing to understand the later stage mergers using galaxy morphology as a tracer of this sort of coalescence event in the merger process. So this is just 6 Hubble images of different galaxy mergers in the nearby universe. And so I'm going to shift now from the introduction about close pairs in their statistics to sort of late-stage final coalescence mergers for the rest of my talk. And so how can we go about identifying distant mergers and their aftermath? And now this is an endeavor that's been going on for decades. There's dozens of image-based measurements that are used in the literature to varying degrees of success. And the standard merger criteria, I think, are pretty good at finding things that are very obviously mergers. So they find things that are obviously two galaxies coalescing or have otherwise severe disturbances. But many merger criteria might miss the lower surface brightness or disturbances that occur when sort of outside of the main light center of the galaxy, and so they're not as if they're fluctuated, they're not going to pick up on sort of these subtler tidal features that we've heard a little bit about today. And so to summarize, the merger criteria that have been used are or can be very pure. You can pick sort of the most obvious things that you see with your eyes or with your algorithm, but they can be highly incomplete, and they may be missing a significant fraction of events that are just too subtle to be detected at with a particular observation. And so this is an approach that I know others in this room are taking, and we're sort of trying to put together a comprehensive set of tools from large hydrodynamical simulations to tease out what this merger rate is from galaxy morphologies in the distant past. And so the procedure we use starts with a realistic sources of mergers and false positives, so galaxies that could look like a merger for other reasons. And so the large hydrodynamical simulations, I'm talking about Illustris today. We forward model them to mock Hubble Space Telescope data to give us a training set or a set of intrinsic mergers and non-mergers that we can use to interpret the real data. And then we learn how to select events. So some people call this machine learning or other kinds of statistical ensemble learning techniques. Basically what you need is a stored algorithm that is based on the training set, which can tell you how to take real data and turn it into number counts or merger rates for that matter. And then the idea is then to take this stored algorithm and then apply it directly to data, and then infer from the catalogs and images that we have from Hubble Space Telescope to infer the merger rate. There's a talk by Mark Huerta's company coming up, which uses the same procedure to look at blue nuggets. Fernando Caro is working on a very similar problem with the Horizon AGN simulation using slightly different techniques. And I know Kamaswara Mantha has thought about this a little bit for his tidal features work. And so I think this is as these new big simulations come online, there'll be more and more opportunities to do interesting studies of processes that are very hard to intrinsically just look at and see what's going on, but you can use the simulations kind of like a filter or a lens to understand what the data are telling us. So what we did is use a set of images that we created in 2015 in collaboration with Paul Torrey from the Illustris simulation, where we created mock HST and JWST images. Here's just an example of like 50 or so out of about 1 million that we created around that time. We didn't actually go in with the idea that we would study mergers or any particular topic. We sort of just created a general purpose data set that turned out to have interesting ability to do studies like this. And then we take work from Vicente Rodriguez Gomez, who you'll hear about later this week, to identify the galaxy mergers via merger trees in the Illustris simulation. And so if we know where the mergers are happening, we can identify which of the sources, which images are real mergers or non-mergers according to some definition. And so in this work, we defined mergers as things that have a 10-to-1 or greater or lesser mass ratio. So these are pretty down to about what we would call minor mergers. And they have a final merger that occurs within 250 million years of the observed time step. And so here's just two examples of the mass evolution versus time for a true merger on the top, and then the mass evolution versus time for a non-merger on the bottom. And you can see the different images over here. The merger in the true merger case occurs about 100 million years in the future in this case. And the thing I want to point out about this is that this is actually a little bit broader than the typical galaxy morphology studies have used to define what a merger is. And so this is actually a pretty ambitious training set in my view. And so there's different ways of doing this, and I think the world is open to us, and we can sort of decide what we want to look for in terms of the level of difficulty here. What we've done is not to do machine vision. We've been using what's called manual encoding. So we're taking sort of pre-existing morphology measurements from the images that we made and using them as input into a random forest algorithm. And so the random forest technique is constructing a group of random decision trees to subdivide the space optimally for a given training set. And so this is a technique that was originally coded up by Michael Peth, who's a JHU grad student, graduated in 2015, is now a data scientist, and Amanda Quirk, who's giving a talk later this week, a summer student in 2016. And so we applied this to our mock images and the merger training set. And so here's just a sort of heuristic of what's happening in the random forest. We have sort of a 10-dimensional parameter space. Here's parameter 1 and parameter 2, and where the mergers and non-mergers might reside within those 2 dimensions. And the random forest simply asks, if I pick one of these parameters at random, say, what point in parameter 2 do I get the purest set of mergers on one side of this separation? And we do that again repeatedly in a Monte Carlo sense. We can map out the space of these parameters in many dimensions. I'm just showing 2, for example, of where mergers are likely to exist given the training set that we have. And so what we end up with is really a probabilistic selection in many dimensions of the morphology space, the catalog space that we've measured from our images. We've cross-validated the multidimensional random forest classifier and shown that it's superior to the technique of just using asymmetry or Gini and M20 alone to select mergers. So this is showing a plot of the completeness versus the false positive rate for our new method at redshift of 1.5. And so what the takeaway message is that we get a sort of a factor of 2 better completeness. So we're accessing more mergers than we can with just a one-dimensional classifier alone, which is nice. But I would say there's still room to go here. We're getting sort of 80% completeness, 30% false positive rate for this admittedly fairly challenging training set. But I think there's lots of different algorithms one could pick. I think we'll hear about more in the next session that would perhaps improve upon this state. Another thing that we've learned is that our random forests are leveraging sort of unexpected information from the morphologies of the galaxies that we input. So they're leveraging different structures at different stages of the merger. So what I picked was a range of about 500 million years around the time of observations. And then we can subdivide that into past mergers and future mergers and ask sort of what our classifier is doing in each of those 2 subclasses. And so here's the morphology measurements down here in the legend. And what we can say is that for past mergers, sort of the things that are merger remnants in the images that we're studying, the bulge signature is actually really important for selecting a merger. So this is the concentration and the Gini M20 along the bulge, sort of the bulge axis of the Gini M20 diagram are very important for past mergers, whereas the classical disturbances like asymmetry and the merger axis of the Gini M20 diagram are more important for future mergers. And that's actually really kind of nice because that's sort of what you would expect for a set of mergers that are selected in different ways at different times. And finally, once we have this random forest set in a way that I think is as good as we could get, given the training set that we had, we went ahead and applied it to data. So Michael Peth and Jen Lotz and others have been measuring non-parametric morphologies from the CANDLE survey. We have these catalogs sort of already in hand. We've measured them in a very similar way to the simulations. And so we went ahead and applied them directly to the catalogs. And we can use that information, knowing how the mapping from the merger cross-validation works in the simulation to back out the merger rate. And so here's the results. This is showing the galaxy merger rate as a function of redshift and as a function of cosmic time. The purple triangles are from the pair timescales analysis that I mentioned earlier in the talk. And the solid curve is the theoretical expectation for galaxies of this mass from Vicente Rodriguez Gomez et al. In 2015. And so what we find from the late stage mergers using the morphologically selected mergers is that we have the same trend. We're rising rapidly to early times at high redshift. We're still uncertain or off by a factor of 2 here. And so I'm trying to understand this at the moment. We have something like twice as many mergers selected from the random forest as we do from the close pairs at the same mass range. And so this could result from a problem or an offset in the morphology distributions between illustrious and the real universe. So for example, I mentioned it's keying off the bulges for a significant fraction of the mergers. This selection, if illustrious is lacking some process for forming bulges, or it's just there's not enough feedback and there aren't enough bulges, it's sort of hypersensitive to the existence of a bulge. This could account for something like this, a factor of 2 more mergers than we would have expected. But I think we still have enough to say that, yes, the galaxy merger rate is rising to early times from data, mostly, with the help of simulations. So around a redshift of 2, we can sort of check this box and say, yes, we think we're seeing hints of this. And this can allow us to sort of understand how these early mergers might then be helping to transform the massive galaxy population. So I'll leave up my summary. Pair-selected merger rates are expectedly high at redshift 2. And simulations plus machine learning and data gives roughly consistent results, at least in the trend. Thank you.
I like very much forward approaches, but I think you raised at the end a very important question, is how you are sure when you transfer from the simulations to the observations that you are doing meaningful things in the simulations that many people know here have many limitations. And the problem with machine learning techniques is that they work very well when you have a perfect match between the training set and the observations. And when this is not the case, they are very bad at extrapolating. And you don't know, it is non-linear, so you don't know how to extrapolate. So do you have any hints on how to cope this? And my one first idea would be to use several simulations, But
totally,
still,
yeah.
it's not a full answer to that, so I don't know.
Yeah, I don't really know. So as Mark mentioned that we don't really know if the simulations are different from the observations in sort of pathological ways, whether our machine learning techniques are leading us astray or not. And I think the simplest way is simply to use as many simulations as we can get our hands on, different assumptions about the models, different training sets selected in different ways, I think is important. But yeah, I think there's also, in the machine learning realm, there are ways of sort of mapping between different parameter spaces. I haven't done anything like that here, but I think there are techniques that could be, if we know the full multidimensional parameter space of the data and the model, we could sort of translate them directly, but I haven't explored that myself.
That's really interesting. So I do have some technical questions. In my experience with running a course, it's super sensitive to recruiting.
Yep.
So have you looked at how the accuracy of the training set is different from second generation network? And then the second question is, with regards to the feature affordances, I also find that they're very sensitive to covariances, so taking a physical interpretation based on the information in the forest can kind of feel restrict of many parameters that can be
Sure. Can you repeat your first question because I didn't catch all of it?
It was overfitting between the tasks and training that I find random
I see, yeah. So in terms of the overfitting, I was careful to make sure that we checked the cross-validation against the test set. And there is some difference in the training set and test set accuracy in maybe the 10 or 20% level. So yeah, that does seem to be there. And there were cases when I was first starting that it was overfitting by a factor of 100 or something, getting right up into the left corner for the training set, and the test set was really poor. But I think we're at sort of the best we can do at the moment. And then your second question was about the feature importances, and I completely agree that I think they're useful as a starting point to try and understand what's going on. But I think more in depth, the fact that they're all sort of clustering in the same way in the sort of intuition that we have about which morphologies are what the morphologies mean is helpful. But I agree, it's not the full story.
So yesterday we heard a talk by Andrew Wetzel showing simulations that indicate that early galaxies are just in lots of little pieces.
Yep.
Are your illustrious galaxies in similarly small little pieces, and would you say that overall what you're finding is rather consistent with his picture?
My hunch is to say yes, that they are in lots of little pieces at these early times. I think the things that we're selecting here at Redshift 2 may be more massive than the Milky Way, and so this may be sort of a different. We didn't go that far low in mass. So these are pretty high mass galaxies that we're studying here, and so these are probably the progenitors of massive early type galaxies in general. But I would assume yes. That's what my guess would be.
Is there a natural way to get at the mass ratios in your way of analyzing the matrix? For example, you could obviously change the threshold from 10 to 1 by going and see how your experiment changes qualitatively.
Yeah, I think qualitatively, to understand the mass ratios that we get out from samples like this, doing different training sets, different algorithms that are stored would be one way to go. I haven't tried that. I've sort of been doing one at a time to keep myself simple, focused, yes. But yeah, you could run random forests with different mass ratio training sets and then just compare them. And I don't know exactly how to interpret the probabilities that you get out there, but there's I'm sure, some information there about the mass ratio distribution.
One last quick question. Keep that.
Yes, we looked into that. So we looked into what the false positives are and physically what they're doing, sort of visually in the paper. So this paper is going to come out be on archive in a couple months, I think. But the basic story is that the false positives a lot of them are mergers that just happen to occur outside of the 500 million year window that I selected. So they're going to happen in 1 billion years or 2 billion years because they're sort of orbiting around each other and they're a projection effect. And so the work here doesn't really take into account projection effects in a very serious way other than for the sort of final stages of the orbit. So that many of them are simply just mergers that happen at a different time. And I don't know how to account for that because you'd like to use that information in your inferences, but I didn't try it.
Okay, let's thank all the speakers in the session. And,